Good afternoon, everyone. Am I audible?
Yes.
Okay. So, today is the ninth interaction session on structural vibration. My name is Devashish Panda. I am a Prime Minister Research Fellow at IIT Guwahati. So, for this semester, I have been allotted as a Prime Minister Research Fellow TA for this course. So, today we will discuss the dynamic analysis of multi-degree of freedom system. So during the last interaction session, we have started the dynamic analysis of MDOF systems, where particularly we have solved the free vibration response of a MDOF system. So today we will spend some time on Rayleigh and Caugh damping model. This damping model are very necessary. We will spend some time on that. Then we will move to the force vibration of MDOF system. Both we will solve in time domain and frequency domain. So first we will see the concepts, and then we will go to the MATLAB and we will solve the response for a MDF system given some input forces or external forces at each degree of freedom. So we will see that. So today let's quickly start. So what I already said that during the last interaction session we have started the multi-degree of freedom system. Multi-degree of freedom system, that means we have more than one degree of freedom system to solve and this system. So during the last interaction session we have learned how to develop the equation of motion for a multi-degree of freedom system. So for example, we have here 3 degree of freedom system, here M3, M2, M1, and corresponding to the column we have stiffnesses K1, K2, and K3. And say for example we have the damping also C1, C2, and C3 we have. And say let's say for the free vibration case already we have solved. So we have developed the equation of motion, that means mass matrix into x double dot or u double dot, whatever you want to write as your degree of freedom, then c x dot plus k. These are the metrics. In matrix already you have seen that within that k matrix what will be the element of k11, k12, k21, and k22, all these things. So kx equals to 0. And also we have seen how to solve for a free vibration response case. So first, whatever we have done, we considered that there is no damping present, say c is equals to 0, and we solved the characteristic equation and find out the mode shapes corresponding to each natural frequencies. And we have seen that the physical response, say x of t, will be nothing but the modal matrix multiplied by your generalized coordinates q or z, right? Or for a particular mode we can write like, for if I want to get at the first mode, say n equals to phi n multiplied by qn. So we have seen that the physical response of a system is nothing but it's the contribution from the all mode shapes. So this is the your modal matrix or mode shape matrix, and these are the generalized coordinates or modal responses. So we have that phi already. We have discussed different properties of the modal matrix, and this is your time dependent, but your mode shapes are not time dependent. They are the time frozen screenshots of the displacements, right? So we have defined the mode shapes. We have seen different properties of the mode shapes, like mode shape is the deflection pattern associated with a particular natural frequency and represents the relative displacement of all parts. So we have solved this system, 2 degree of freedom system, and we have found out that this is my first mode shape, that means phi 1, which will have two component, phi 1 and phi 2 1. Again we have this phi 2, that means second mode shape corresponding to second natural frequency. So we have phi 1 2 and phi 2 2, right? And already we have I have said that okay, that mode shapes are the inherent property of the structure. It actually doesn't depend on the loads or the structure. It will vary only when the natural frequency will vary. That means the parameter of the natural frequency will vary, then it will vary. That means mass and stiffness property will vary, then it will also vary with simultaneously. So and also we have seen the structure of the modal matrix. I already have said okay, phi, this actually contain the information of the all mode shapes. So let's say we have n number of mode and we have j number of DOF. So the modal matrix will look like this. So this is the structure of the modal matrix. That means each of its column contain mode shapes. Say this is your phi 1, and again go to the next column, you will get your phi 2. So phi 1 content phi 1 1, phi 2 1, phi 3 1 dot 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 phi n1. Similarly, so within that modal matrix we have the mode shape information. So this is your first mode, this is corresponding to second mode, this is corresponding to third mode, and all these things. And also we have discussed that if we have this diagonal matrix where only the diagonal term will consist the corresponding natural frequencies. That means in a way, if we normalize the stiffness matrix phi transpose k phi, so we will get m phi and omega r squared. So omega r squared, that means so m matrix phi and omega r squared. So omega r squared, that will contain the natural frequencies, and we call them the spectral matrix. So and by this way, by using modal and spectral matrix, we can write that characteristic equation in the terms of k phi is equals to m phi omega square. So all these things we have already discussed, and also we have discussed the orthogonality property of the mode shape. What I said, like k is equals to phi transpose k phi and m is equals to phi transpose m phi. So ultimately, what will become, say, the mass matrix when we will normalize with the mode shapes or mode normalized mass matrix. So first thing we will look for the modal mass. So this is nothing but phi transpose m phi, and it will be a diagonal matrix. And again, what I said, that k, if I want to normalize it with modes, then k will be normalized. This is the modal stiffness matrix or normalized stiffness matrix will be phi transpose k phi, and ultimately k is equals to phi transpose k is equals to omega n square m, or m omega n square is equal and your phi. So ultimately we will left with omega n square phi transpose m phi. That means it's nothing but the modal matrix. So omega n square and m, and m, this is like normalized mass matrix. We all know this will become identity matrix. So we will left with omega n square. That's why we call it a spectral matrix, right? Then we have seen that how to normalize the mode shape with respect to amplitude. If we want to normalize the mode shape with respect to amplitude, say for example, we need to normalize the last degree of freedom to 1, then how we can do that? It's easy. So we just need to normalize it to 1. And mass normalization, this is very important property we also talked about. Like generally for computational purposes, like if we go with mass normalization, then the computational effort will be little less. So the mass normalized matrix or modal mass matrix is nothing but your phi, that means spectral matrix, into m into phi. So each component of this matrix will be mn, that means phi n transpose m phi n, right? That will contain the diagonal term of this matrix, and this will actually become an identity matrix I. That means all of the component, like if I want phi n transpose m phi n, so it will become one. That means to get that mass normalization mode set, you need to follow this property, like phi n transpose each of the component of this modal mass matrix will be 1. That means basically it will become the identity matrix. So we will see how we can do that normalization things. And here again this part, like the spatial matrix phi transpose k phi will become like m and omega n square. So ultimately it will become omega n square. So the modal stiffness matrix k will contain say omega 1 square, omega 2 square, omega 3 square in diagonal term. Okay. So these are the very important property we need to remember. These are very helpful to solve different kind of problems. Okay. Then we move to the during that last interaction session we move to that response of a undamped free vibration system, where we have seen that physical response u of t is nothing but say if I want to consider the effect of all modes, then it will be phi n qn, and the equations will look like this. Like if we want to expand the equation as per the degree of freedom, we will have u1 u2 u3. So basically the response x of t, so this is vector, that means it will contain the response of corresponding to all degrees of freedom is nothing but the mode shape matrix phi, the big phi, the mode shape matrix. It's not only a single mode shape. The column of this modal matrix will represents the all mode shapes and your generalized coordinate q or z, whatever you want to uh, denote. So in modal coordinates, if we have the modal response and the mode shape information, we can easily find it out the response of a system. And by this way, like for a free vibration system, we can calculate the qn, the generalized coordinates or the modal response, an cos omega nt plus bn sin omega nt. And here we have defined the initial conditions like an and bn. We can find out from the initial conditions. And finally, uh, the complete solution u of t is nothing but your generalized coordinates and mode shapes. We have solved for this. Now for the dam system also similar kind of thing. Like first you need to find out the equation of motion, and then you need to find out the mode shape. Once you have the mode shape and generalized coordinate information, like for a damped free vibration case, we know what is the generalized response or the modal response. Qnt is equals to e to the power minus zeta n omega nt q0 cos omega dt plus q dot 0. Already we have solved when we solved that single degree of freedom system. For if you recall that condition, you will find out that okay, x of t we have solved like this. X of t was e to the power minus zeta n omega nt, say a cos omega dt plus b sin omega dt. And here a and b find out from the initial conditions. That means what is the value of uh, the response, that means the displacement at t is equals to 0, and what will be the velocity at t is equals to 0. From here we have found out the responses. Once we have the information about the generalized coordinates, we can easily find out the displacement response. Displacement response is nothing but ut will be equals to summation of I is equals to 1 to n phi n qnt. Like here if you see the structure, you can see that this u actually content u of t is a vector. It contains information about each degree of freedom u1 u2 u3 is equals to phi matrix. Say phi matrix content what? The modal information. That means your first mode, second mode, third mode multiplied by your generalized coordinate q. Say for example here we have three degree of freedom, and we have like three mode shapes. So here physical response of u1, u2 and u3 will be, this is my modal matrix. So if I want to write down the modal matrix, so first I need to write down the first mode shape, that means phi 1 1, phi 2 1, phi 3 1. Recall the structure: phi j n. J is your degree of freedom and n is the which mode you are considering, the mode you are considering here. So 3 1 again. For the second mode, phi 1 2, phi 2 2, phi 3 2. Again phi 1 3, phi 2 3 and phi 3 3. And q, it's like q1, q2 and q3 for the modal responses corresponding to three modes. Now if you equate, your u1 will become phi 1 1 q1. Just do the matrix operation: phi 1 1, like multiply in that direction, phi 1 1 q1, phi 1 2 q2, phi 1 3 q3, so on. So now if we want to calculate the response of the second degree of freedom, then again similar kind of equation, and finally this equation look like u of t, it's a vector, is equals to summation of I is equals to 1 to n phi n and qn t. That means if you have you need to consider the two modes, then that will be phi 1 q1 plus phi 2 q2. If you have three modes, subsequently the equation will uh, get larger. So this how the structure of the modal representation forms. So like here, how we can solve it? Easy. First you need to calculate the mode shape from the characteristic equations, and then from the initial conditions you need to find out what will be the initial q, that means the modal responses, and then once you have the modal responses, you can find out the physical response of the systems. So we have already talked this, cover already done this exercises, but today like why I started with this thing, like a few examples related to this week, actually related to that concept. So like let's quickly solve one example. Already we have solved like how to calculate the mode shapes, how to normalize them and all these things. So we will see how we can get the first that mass normalized mode shapes, because a few questions may come from this mass normalization thing. So pay attention to this question. Like here we have a system. Determine the natural frequency and mode, or the mode shape of this system, and normalize the mode so that mn will be 1. Mn, that means what is that mn? It's the element of the normalized mass matrix or modal mass matrix. That means here we have m1, here we have m2, here we have m3 dot 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 mn, that means phi n transpose m phi. Just you need to make it like that. So that means what they want, they want you should normalize the mode shape with respect to mass. That means we need to have the mass normalized mode shapes. So let's okay, start this example, like how we can solve this example. First we need to create the or construct the mass matrix. So here we have two degree of freedoms. First degree of freedom u1 and u2, right? And corresponding to first degree of freedom, we have mass 2m, and for the second degree of freedom, we have mass m. So our mass matrix always it's a diagonal matrix. So m is equals to 2m 0 0 m. And for K matrix, we know for the two degree of freedom system, the K matrix will look like the coupled K matrix K1, then minus K2, minus K2, K2. Or so here, so just think K1 plus K2 or K2, K1, and like from this equation of motion already we have derived it for two degree of freedom system. So recall this uh, K matrix. If you can formulate the K matrix at a very first place, then the entire problem will be wrong. So the first element I'm written here wrong. Like the first element is K1 plus K2 minus K2 minus K2 K2. Right, Sovik?
Yes.
Yeah. So K matrix, or if you forget it, just you should I will recommend you should recall this pattern of this matrix, so it will be easy to solve this problem. So the structure of the K matrix for a 2 degree of freedom system look like K1 plus K2 minus K2 minus K2 K2, right? So now we have the K value. K1 is given as K1 is given as 2K and K2 is given as K. So K1 plus K2 become 3K minus K2, that means minus K minus K K. So we have formulated the stiffness matrix also. Now what we need to do? We need to solve the characteristic equation. That means we need to find out the determinant of the characteristic equation, and that is nothing but K minus omega square M is equals to 0. So we have K matrix, we have M matrix. Now we can easily solve this matrix problem. So K matrix, you just write it down, 3K minus K minus K K minus omega square, and we have the M term 2M 0 0 M. Now you need to find out the determinant of this matrix, right? So here is the calculations, and once you have solved this, you will find out two roots of this omega square, like omega 1 square and omega 2 square. So omega 1 square comes as K by twice M. So omega particularly, so we have omega 1 square, that means the first root of this characteristic equation comes as K by twice M. And we can find out the omega is nothing but under root of K by twice M. Again, find out the root, second root, and the second root comes as 8K by M. 8K by M. Omega 2 square comes as 8K by M. That means omega 2 also we can find out under root of twice K by M. Right? Now our goal is to find out the mode shapes and normalize the mode shape with respect to mass. That means we need to do that mass normalization things. So we have now our omega 1 and omega 2 square values. Now corresponding to omega 1 square and corresponding to omega 2 square, we need to find out the mode shapes. That means it's a simple eigen value problem. We already have found out the eigenvalues. We need to find out the eigenvectors. So corresponding to omega 1 square, in this equation, what you will write, instead of omega, first omega 1 square write, and then solve the equation. So here corresponding to omega 1 square multiplied by first mode shape. First mode shape, that means phi 1 1 and phi 2 1. Okay. Now here, if we simplify this, we will left with this equation. Now for the last mode, we normalize it to 1, like 1, and what will be the value of phi 1 1? We can find out 1 by 2. So phi 1 comes as 0.5 and 1, first mode shape. And second mode shape, again replace omega 1 square by omega 2 square and do the same exercise. You will find out that phi 2 2 is 1. That means the top mode we have normalized to 1, and phi 1 2 comes as minus 1. So the mode will look like this. So this is your phi 1, this is your phi 2. This value is 1, this value is minus 1. Right? Now we have the mode shape now. What the question asks, you need to normalize it with respect to mass. So how we can do the mass normalization? So for the mass normalization thing, we need to follow this like phi n transpose mass matrix M. This is the normal mass matrix, not normalized or anything. Phi n should be 1. That means what that actually means, this is the Mn, nth component of the normalized mass matrix. That means modal mass matrix. So what do we need to do? We have the mode shapes. So we what we need to do? We need to normalize it like phi 1 normalized with mass is nothing but the vector, that means my phi 1 divided by this component under root of this component under root of Mn. That means phi 1 under root of phi 1 transpose, because n we are doing it corresponding to first mode. So phi 1 transpose M phi 1. Now do the exercise and simplify it. So phi 1, we need to find out the value of this. So the value we can easily calculate because we have the phi 1 value, half and 1. We have the mass matrix. So the M1 component comes as 3 by 2M. Now phi 1M, that means normalized thing will be 1 by 2 1. This is phi 1 divided by under root of 3 by 2M. And what is the 3 by 2M? It's nothing but the after calculation phi n transpose M phi n. So this is 1 by root 6M, 1 by 1 and 1 and 2. This is your mass normalized mode shapes. For phi 2n M, again, what you need to do? You need to calculate phi 2 divided by under root of phi 2 transpose M phi 2. So you will get the second mass normalized mode shapes. Now, how to check them? You can check it like your mass normalized mode shape comes as this. So you have the modal mass matrix M. So you will get that this condition, if this condition satisfies, okay, the normalization is done, right? So if some question asked like mode shapes are given, mass matrix are given, how to normalize the mode shape with respect to mass, that's why we can normalize it. Like uh, vector, how to normalize a vector? We have like a vector, say for example u vector. I need to normalize it with respect to say length, so or that magnitude of this vector. So what I need to do, the normalized part will be that vector itself u divided by Euclidean norm of u, and Euclidean norm of u means under root of that particular vector. So already we have discussed these things here and we have solved some examples also like here. So by this way we can mass normalize the mode shapes also. Now what I said, like we will spend some time on this damping models, because these are very important when we will model some multi-degree of freedom system. So obviously we have seen that okay, we have the mass and stiffness matrix. We know if damping is not present, how to uncouple them from the coupled equation, and if like there are n number of degrees of freedom, how we can use the damping model. So we talked about Rayleigh damping model. Few things we have already uh, discussed about this Rayleigh damping model. So this Rayleigh damping model, actually the model is very simple, like C is equals to A naught M plus A1 K. That means he has proposed one you know one relation with mass proportionality and also the stiffness proportionality thing. And this model will only work when all the roots are real and positive. That means it, that condition C M inverse K should be equals to K M inverse C. If it satisfied this condition, that means my roots, all the roots are real and positive. Then only I can apply this model Now we will see how to damping ratios, modal damping ratios can be calculated, and how we can implement this model. So here what I said, like it has two component. One is like the damping mass proportionality part, and one is the stiffness proportionality part. So let's quickly go through that mass proportionality and stiffness proportionality part. So here that C is given as A naught into M. Now if we pre-multiply with phi n transpose C phi n is equals to, again, phi n transpose A naught phi n M. So what will we have, like Cn normalized damping matrix will become A naught into phi n transpose M phi n is nothing but your Mn. So Cn comes as A naught Mn, right? Now we know that zeta, damping ratio zeta, is nothing but C by CCR, and CCR we know twice M omega n, right? So now instead of Cn, if we replace this A naught M, so zeta n will become A naught by twice omega n. Okay, m and mn will cancel out. Now A naught will be nothing but twice zeta omega n, and we know that CCR is nothing but that critical damping ratio. Critical damping ratio means that the amount of damping needed to completely diminish the vibrational energy from the system. So it's not like CR is equals to twice M omega n, but we have found out, okay, A naught is twice zeta omega n. That means A naught is proportional to your omega n, right? That means the proportionality constant related to the mass will directly proportional to the omega n. We need it because, like, first uh, go through that stiffness proportionality, then we will combine these two. So stiffness proportionality part, we have seen that Cn is nothing but A1 into K. Now if we expand it, K is equals to, we know, like M omega n square. So A1 omega n square Mn, right? Now we know zeta is equals to C by CCR. So if I write it down, A1 omega n square Mn by CCR is nothing but twice Mn omega n. So from here we can find out, like A1 is nothing but twice zeta K by omega K, right? Or omega n, whatever, if you want to indexing it. So here we can see that A1, the stiffness proportionality constant, is inversely proportional to your omega K. Now I have A1 value, I have A naught value. Now I can easily construct this model. So C is equals to A naught M. A naught already we have found out here. A naught is equals to twice zeta n omega n. That means it's directly proportional to your omega n quantity. So now we can write it down like this: zeta n is equals to A naught by twice omega n plus A1 omega n by 2, right? Now in a matrix form, how we can write it down here? If we have like ith and jth modes, consider ith and jth mode, so I can write it down like 1 by omega I, 1 by omega j, a naught a1 is equals to 2 zeta I zeta z, right? For 2, say for example here For first and for the second degrees of freedom, the zeta is given as zeta 1. I can express is a naught by twice omega 1 like omega I, a1 omega 1 by 2. Now in a matrix form, if you multiply it with 2 like in this way, so what we will left with, like zeta I is equals to a naught by twice omega I plus a1 omega I by 2. So in a matrix form, we can write the damping ratios, and we can, if we have that ith and jth damping ratio, we can find out the damping ratios for the third modes also. So if we have n number of modes, we can write down the equations. Now the problem with this model is, like here we can see like two unknowns are there. So that means we need to specify for damping for first two nodes or any two consecutive nodes. It will calculate the damping ratio for the third node. But like if we need to give the input as a like zeta 1, zeta 2 and zeta 3, for the three modes we need to give the input, then this model will not work. Say for example, here this system, we have a 3D DOF system. We have mass 200, 400, 400 kg, and the corresponding stiffness are also given. So here, consider that zeta is equals to 5% for first and two modes. Now calculate the or construct the C matrix. That means in your C matrix, the third also, the damping information about the third mode also will be there. So how we can do that? So here first we need to solve the characteristic equation and find out the omega I. So first natural frequency comes as 12.57, second 34.3, and third is 46.3 rad per second omega i's, right? And corresponding mode shape also you need to calculate. Then we can apply the model. So zeta n, we have the model zeta n is equals to a naught by 2 1 by omega n plus a1 by 2 omega n. Now in a matrix form, how I can write it down? Like 1 by omega 1, omega 1, 1 by omega 2, a1, a0, a1 is equals to 2 into, for the two modes, we have the damping ratio, zeta 1 is equals to 5% and also zeta 2 is equals to 5%. Now, if we solve it, we can easily solve a0 and a1, right? So here a1 comes as this, a0 comes as this. Now we can find out the what will be the zeta 3. Zeta 3 is nothing but a naught by 2 1 by omega 3 plus a1 by 2 omega 3. Now you can calculate the value of zeta 3, and once the zeta 3 is there, you can easily calculate. So zeta 3 comes as like 5.89%. Now once the zeta is available, you can formulate the model. C is equals to, alpha m plus beta k, or a naught m plus a1 k, and you will find like the symmetrics or construct the symmetrics. Damping ratio, if you can find out the damping ratio, you can easily construct the symmetrics. Now the thing is, like for, say for example, we have that again this multi degree of freedom system where it has three modes, m3, and zeta 1, zeta 2, zeta 3. So zeta 1 5% we have considered, zeta 2 5% we have considered. It calculates the zeta 3 as 5 point, say something 38%. Now, say for example, I need to I want to provide the input for all these three modes. Then what will happen? Then, or I need to provide the input for ith and jth node. Or say for example, it has multiple degree of freedom system. How I can go with that? So we have another damping model called that Caugh damping. It's also similar kind of thing, but it has more terms. So the damping model, he has proposed C is equals to nothing but M, L equals to 0 to n minus 1, AL M inverse K to the power L. This is the damping model or the Caugh damping model. What was the Rayleigh damping model? Recall C is equals to A naught M plus A1 K. Now here, if I make L is equals to 0, then C only left with A naught M. Only we have the mass proportionality part. Yeah. And if I make L is equals to 1, what will happen? We will have A1 K term, right? Now L equals to 2, you can have A2 M inverse K. Just put all this part in this equation. You will find out that the term of this like coefficient term will increase. So if we use this equation like here, if I want to use these two terms, I can add them up. Say C is equals to L is equals to, we will consider 1. So it will have L is equals to 0, L is equals to 1, two parts. If I consider L is equals to 2, say L is equals to 0, 1, 2, 3 parts. That means A0M we will have as per this, A1K again as per this, and next term. Okay. So ultimately, these proofs are there. It's very simple, like how ended up with this. They are very simple and straightforward. You just go through it, you will see. Just pre-multiply with some mode shapes to use that modal orthogonality property and solve it. Now the zeta n model, the model zeta n will look like this. Say zeta n for this model, have just recall this model. Okay, I remember this model, sorry. L equals to 0 to j minus 1 or n minus 1, a l w n 2l minus 1. So this is the model of the Caugh damping. Now in a matrix form, we can easily arrange them. Like here, for the same example, whatever we have considered there, we have considered like for the first two modes, zeta 1 is equals to zeta 2 is equals to 5%. Now let's consider I want to give the input zeta 3 also 8%. Now construct the symmetrics. Until or unless we can construct the symmetrics, we cannot solve the system, right? So how we can solve it? The zeta model, using this Caugh damping model, we can solve it. Zeta n is equals to nothing but, so for the three modes, the C will become A naught M plus A1 K plus, again third term we will consider A2 K M inverse K. So the zeta n model will become A naught by 2 1 by omega n plus A1 omega n plus A2 by 2 omega n cube, right? So in a matrix form, how I can represent it? So first term, say for example, I want to write it like this with respect to the unknown variables A naught, A1, A2 is equals to twice into say zeta 1, zeta 2, zeta 3. That means I want to take this 2 on this other side. So how I can write 1 by omega n or omega 1. So for the three modes, if I want to write 1 by sorry, omega 2 and omega 1 cube for the first mode. Now 1 by omega 2, omega 2, omega 2 cube. Now 1 by omega 3, and again omega 3 cube. Now once you have this matrix equation, you have three unknowns, you have three sort of equation, you can easily solve this equation. So ultimately A1 will become 1.08, A2 becomes some 9.14 into 10 to the power minus 4, and A3 become 9.17 into 10 to the power minus 7. Now once you have this A1, A2 and A3 information, you can easily calculate the symmetric. C is equals to nothing but A naught M. You have the M matrix plus here the equation A1K plus A2K M inverse K. Last term comes from here. If we consider that L is equals to 2, it comes as A2 M inverse K, right? Okay. So by this way, we can use the damping model. So we will see, we will code one MDOF system and use that Rayleigh damping or Caugh damping model to calculate the modal damping ratios, and we will solve the system. So we will do that exercise in few minutes. So first, now we will move to the force vibration part. Now we have the concept of damping, how we can use the damping models and all these things. So till now, do you have any questions? Okay, so like now that force vibration part, that means uh, this MDF system can subjected to the external dynamic forces at each degree of freedom, or it may have particular applied at the particular degree of freedom. So ultimately the equation of motion will look like M, the mass matrix, x double dot plus k x, I miss the damping term, c x dot is equals to your force matrix, right? It's actually the vectors, force vectors acting at a particular nodes. Now, how we can solve it? Again, in the model representation, we will solve it. First, this is the equation of motion. Here, I have considered like, say, let's say 2 degree of freedom system. So here, at each degree that external load is applied, F1T and F2T. At a degree of freedom x1, the load is F1T, and at degree of freedom x2, the load is F2T. So now we know that x, the physical response x, is nothing but the modal matrix phi into the generalized coordinates q or z. Q or z, both are the modal response or the generalized coordinates modal responses. Okay, so now use this transformation, replace all this part in this equation. So what will happen? We'll have m phi z double dot plus c phi z dot plus k phi z equals to f. Now pre-multiplied both side with phi transpose. So phi transpose m phi z double dot plus phi transpose c phi z dot plus phi transpose k phi z is nothing but phi transpose ft. Now we know, already we have discussed, like phi transpose m phi is nothing but the modal mass matrix, right? And it actually becomes identity matrix. And already we know that phi transpose k phi is nothing but your modal stiffness matrix, it's diagonal. And for the damping, we have considered the classical damping part. That means we have considered that all the roots are will be positive and real. So ultimately, C matrix we will form using this model. So the Rayleigh model, A naught M plus A1K. Now again we can get the modal matrix. It's nothing but phi transpose C phi is equals to C. It's also a diagonal matrix. Modal damping matrix, or it's also a diagonal. Right? Here, like mass normalization of the mode shape, it's nothing but phi n into that modal mass inverse, that means the inverse matrix, that means divided by, you will get the mm, component of the normalized mode shape. Okay, so now if we further simplify this equation, what we'll have, we'll left with that m, and also this phi transpose ft, this is called the modal force, right? Now finally, if we use that property, like we left with this equation, we you know categorize this modal mass matrix, stiffness matrix, and modal damping matrix, and these are the diagonal matrix. That K, like modal stiffness matrix, the element of this modal stiffness matrix will be nothing but like omega 1 square, omega 2 square, and all these things, because the mn will be 1. Already we have discussed this thing. So here simplified version of this part will be I z double dot, because this MD matrix, modal mass matrix, become the identity matrix. That C matrix, the each component of the C matrix will go C, that means modal damping matrix phi transpose C phi will become like each component, say twice zeta 1 omega 1 twice zeta 2 omega 2 dot 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 twice zeta n omega n. We will have the matrix in like that. Now for each if we separate out the matrix into equations, so for the each mode we will have this model representation like this: zn double dot plus twice eta n omega n z dot omega n square is equals to fnt. Fnt is the modal forces. We can calculate it is like this: j is equals to 1 to t 1 to n phi nj t. N is the number of mode shapes, j for corresponding to which degree of freedom. So this system has some initial condition in the physical domain. How we can find out the initial condition in the z domain, like in the modal coordinates? So it's very simple. We can do it in two ways. Like first, we know already x, the physical response is nothing but phi into z. So obviously at t is equals to 0, x naught is nothing but phi into z naught. Now z naught is nothing but phi inverse of x naught, and z dot naught is phi inverse of x dot naught. So we need to do the inversion thing. One way we can also do it, like we again know x is equals to phi into z. So at t is equals to 0, x naught is nothing but phi into z naught. Now use that modal mass matrix and pre-multiply with phi transpose. So phi transpose m x naught is nothing but phi transpose m phi z naught. Now phi transpose m phi, this become 1. So z naught is nothing but phi transpose m x naught, and z dot naught is phi transpose m x dot naught. So by this way, by one of these two ways, we can calculate the initial conditions for this case. Now once we have the initial conditions, modal information, we need to find out the modal responses. So modal responses for a force vibration system, we have seen that it contains two parts, the complementary part and the particular integral part. So complementary part, which cater the free vibration part, already we have solved. Zn is equals to e to the power minus eta n omega n t, a n cos omega dt, b n cos omega dt, and this is the particular integral part. It's nothing but the impulse response function and the forcing function. From the dual integral already we have solved it, right? So once we have all this information, we can easily calculate the value of the responses or the physical responses. Say for example, using the Duhamel integral, if we want to solve it, so recall using the Duhamel integral, the Zn or the impulse response function, recall that that I, and from there the responses we have already calculated. So 1 by uh, omega d e to the power minus eta omega n sine omega dt. These are the responses. And if we, for the unit impulse, and if we have the force Fn, just multiply with Fn, you will get the Zn. Now once we have that Zn, and say let's say we have a particular the load, the impulse is acting on a particular degrees of freedom or corresponding to a particular degree of freedom. Say for example here, if I want to say like force matrix here, let's say we have 3 degree of freedom system, but the force is acting only the second degree of freedom system. So what do we need to do? We need to incorporate one matrix which will give that direction. Say for example 0 1 0, and then we will have this F matrix. So obviously for corresponding to that degree of freedom, the force will acting, and for the rest of the system you will not consider. So finally the physical response x of t, or x say I of t, is nothing but summation of n equals to 1 to n phi in Zn of t. That means if we can calculate the modal responses using using the Duhamel integral, and we have the mode shapes, we can easily calculate the responses of a multi-degree of freedom system, and we will solve it using the MATLAB. We will see how to do it. Right, so do you have any kind of questions? You can ask me, or we can solve first this within MATLAB, and then we will move to that assignments part. Okay then, so let's quickly solve this solve the assignments, and then we will move to the MATLAB part. Okay, so now we have the, like, this is Duhamel integral. We have already seen that this is the time domain solution of the system. So this is how we can do the time domain solution. Like, instead of this Duhamel integral, we can use different numerical technique to get this hidden, like numeric beta, Wilson theta, and all these things. So we will see, and during the due uh, uh, course of this sessions. Okay, now let's say if we want to solve the system in frequency domain, so what do we need to do? We also know how we can convert one signal from time domain to frequency domain, and frequency domain to time domain, vice versa, using the Fourier transformation pairs. So here you can see x omega and xt. That means the response at the frequency domain is nothing but 1 by root 2 integration minus infinity to infinity xt to the power minus I omega t dt. And xt, if we want to get the responses at time domain, it's nothing but 1 by root 2 minus infinity to infinity x omega e to the power I omega t d omega. Now how we can convert this equation to frequency domain? So we have the equation of motion, mx double dot plus cx dot t plus kx dot is equals to ft. Now xt, we know this relation, so just now insert all these relations, all these things, or replace all these things, substitute all these things here. So finally we will leave with this equation, 1 by root 2 minus infinity to infinity k minus omega square m plus ic omega x omega is equals to 0. And finally we have this equation, k minus omega square m ic omega x omega minus f omega is equals to 0. So here x omega, that means the response at frequency domain is nothing but h omega into f omega. That means this is your frequency response function, frequency response function, and this is forcing function at frequency domain. So h omega, this part is called the frequency response function h omega. So h omega is nothing but k minus omega square m plus ic omega inverse, right? Now, if we have, in degree of freedom system, we can construct the K matrix, we can construct the M matrix, we can construct the C matrix. So here, if we want to if we want to get the solution directly using this method, we need to, invert this part H omega for every omega. So it will be little computationally heavy. Rather, if we can, express this in a modal uh, coordinates, so we don't need to do the inversion term. So here we can see that, okay, in the likewise your single degree of freedom system, the response in frequency domain is nothing but the frequency response function and frequency domain into the force in frequency domain, and H omega we can find out that what will be the frequency response function. If we have the system matrices like K, M, and C, we can easily formulate it. Now, how we can, express it in the modal coordinates, so that we can replace this inversion, right? So here we can see again we have this similar kind of relation, transformation relation. X is equals to that physical response is nothing but phi into Z. Now we have some orthogonality property about the matrices, like already we have discussed that phi transpose this phi are the big phi. Okay, modal matrices, not the mode shapes. M phi is equals to I. So these are all will be the big phi. So big. Okay. It's not the mode shapes, individual mode shapes. It's the modal matrix which contain all the information of the mode shapes. Then only it will become identity matrix. Otherwise, if we consider that phi n transpose m phi n, it will be become 1. That means the component of this matrices, right? And also we know phi transpose k phi is nothing but your omega square matrix, right? And it's also the diagonal matrix, the diagonal term of this will coordinate. And also the modal stiffness matrix phi transpose damping matrix C phi will become the diagonal matrix with term twice zeta n omega n, right? Now, if we have this orthogonality property and relations, we can easily use this transformation. So here we have used this transformation. The equation will look like this, like k minus omega square m ic omega phi. Instead of x omega, I have used phi into z omega. Now pre-multiply with phi transpose both side, phi transpose and phi transpose. So we will left with like phi transpose z omega, and we have the phi. Within the bracket we have ic omega m and k. Now using that phi transpose k phi, phi transpose m phi, phi transpose c phi. Now just use these matrices here. So phi transpose k phi is nothing but the diagonal of omega square. Then phi transpose m phi become the identity matrix. Phi transpose c phi become the diagonal matrix having the term twice zeta n omega n in each component is equals to f transpose f phi transpose f omega. So this is your final equation. Now we can easily find out the what will be the responses. Zn will be nothing but summation of k1 to n phi nk transpose fk divided by omega n square minus omega square plus I omega eta omega omega n, right? How I get these things? I get these things after, putting all the matrix value in this format and solve it, so you will get the equations. Now once you have the zn values, you can easily find out that x omega will be nothing but phi. This is big phi, all are the big phi's. Okay, that means the modal matrix or the mode shape matrix, not only the mode shapes, they are vectors, right? So once we have that all z n in frequency domain, we can find it out phi into z of omega. This will be the response at frequency domain. So by this way, like here if we use this approach, we don't need to invert that h omega at each time point for every omega. Instead, we just can calculate all the things using the modal information or mode shape information, and it will be computationally little heavy or little less heavy, right? So by this way, in time domain as well as in frequency domain, we can calculate the responses or the physical responses of a MDOF system like this. So do you have any kind of questions, or we can move to the assignments part and then we solve the in MATLAB we will solve one example of multi-degree of freedom system. We will see how we can implement it and solve it using MATLAB. So do you have any questions?
No. No.
But you need to make all these files big files, okay? There are a basic difference between the modal matrix and mode set matrix. You got it, no? That's why I'm telling that all notation should be big file. This big file. This is the modal matrix which contains all the information of the mode shape. Each of the column represent the each of the mode shape. That means small phi n. Phi 1, the first column of this big phi. And here we have used that matrix notation and matrix thing. So all the phi we have written here will be the big phi's. Okay, like this one, big phi's. Okay, then let's quickly solve few examples and then we will move to the MATLAB and we will see how we can solve this. Okay, so the first question, be careful with the questions. I have changed the data. These are not direct form of the assignment questions. Similar kind of questions are there in the assignments, but I have changed the data a little bit. Okay, so the mass, be careful with that. I have changed the data. So the calculation procedure will be same. You just need to calculate with your data, then you will get the same kind of answers. So the mass and the tutorial 4, already you have solved 3 tutorials. So tutorial 4, the mass and stiffness of a MDF system is given. So mass matrix is given as 800 0 0 400 kg, right? That means we have two DOF system. M1, M2, K1, K2, right? Mass matrix is given. K matrix is also given. Already they have assembled K1 plus K2 minus K2 minus K2 and K2 and given as this. Now the mode shape matrix phi is also given. Look, the phi is here. The notation of phi is correct. Big phi is given. That means phi 1, the first mode shape is 0.51 and phi 2 is minus 1, 1. Right? Okay. The force acting on the system is given as Ft. 25 sine 20t, 10 sine 20t. That means in each degree of freedom, we have two forcing acting. So here this F1t is acting. That means 25 sine 20t, and at here 10 sine 20t is acting. The forcing frequency 20, right? Now, first, what then one? Calculate the mass normalized mode shape for all modes. So we have two modes. First mode, second mode. The frequencies are not given, but the mode shapes are given. Great. So what I need to do? Calculate the mass normalized mode shape. Mass normalized mode shape. So mass normalized mode shape, we know phi 1m. Already we have solved one example related to that. So phi 1 divided by under root of phi 1 transpose M phi 1. Phi 2M must normalize mode say phi 2 under root of phi 2 transpose M phi 2. Now you just need to do the calculations. What that component? Phi 1 transpose M phi 1 and phi 2 transpose M phi 2. This and this, right? That means if we do the calculation with respect to the mass matrix, we can easily find it out. So what will be the modal mass? M is nothing but phi transpose whole thing, M phi. So phi transpose phi, that means the modal matrix already given. This is your mass matrix, and again this is your modal matrix. So phi n transpose M phi. So we will have this matrix. That means this component is nothing but phi 1 transpose M phi 1. If you do the separate calculation, you will find this is nothing but phi 1 transpose M phi 1, and this is nothing but your phi 2 transpose M phi 2. So we have these two values. We have the modal information. So what will be the mass normalized mode shape? First mode shape is phi 1. The value of phi 1 is 0.51 under root of 600. So this comes as this mass normalized first mode shape. What will be the second one? Phi 2. Phi 2 already we have minus 1 1 under root of phi 2 transpose M phi 2, and that comes as 1200. So under root of 1 by under root of 1200 minus 1 1, that comes as this. So these two are the mass normalized mode shapes. Clear? Now let's move to the next question. Same question. Now calculate the modal frequency. Look, the frequencies are not given. So calculate the modal frequency. We can calculate the modal frequencies easily using that, concept of that spatial matrix, like phi transpose k phi is nothing but we will get omega n square matrix, right? So we have the value of phi 0.51 minus 1 1. We have the value of k 10 to the power 10 to the power 5 5 minus 2 minus 2 2, and the unit is Newton per meter. If it is given kilonewton per meter, you need to do the conversion similarly. So now if I do this operation, I will find out this omega n square matrix, and it will be diagonal matrix. So do this matrix operation. You can use it MATLAB. It will give the answers within a second, or you can directly, like it's a 2 by 2 matrix, you can easily do the calculations. So after calculation, that is my omega 1 square, this is my omega 2 square. So what will be the omega values under root of these two? That comes as 14.43 radian per second, 0, and 30.27. Great. We use the orthogonal property of the modal stiffness matrix, right? How this actually happen? Like phi transpose k is equals to, m omega n square into phi. Now phi transpose m phi omega n square. Now phi transpose m phi, it's the identity matrix. So we left with omega n square. By this way, we can calculate the modal frequencies corresponding to that mode shapes. Clear? Now let's move to the third question. Continuation of the same question. It says calculate the generalized forces. We have given the forces, like at first node we have given 25 sine 20t, and in the second node 10 sine 20t. So these are the external forces. What will be the generalized forces? The generalized forces, we know Fn of t is nothing but phi n transpose f of t. So we have, for the first mode, f1 of t is equals to phi 1m. That means the with respect to that you know mass normalized mode shape, using, they have said mass, you need to use the mass normalized mode shape, and we already normalized the mode shape with respect to mass, and we have the values. This one is the first mass normalized mode shape, this one is the second mass normalized mode shape. So phi 1 t, phi 1 mt into ft. So you have this value, this is already we have calculated 0.0204 and 0.0408, 25 sine 20t and 10 sine 20t. And if you do the uh, calculation, you will find 0.92 sine 20t. So the matrix operation, like multiply this and this. So this multiplied by this plus this multiplied by this, you will get this. For the second mode again, phi 2m, that means second mass normalized mode shape multiplied by the force vector, we will have this. So these are two Fn of t. So this vector content two modal information about the force 92 sine 20t and minus 0.43 sine 20t. So these are the modal forces. Great. Now again we have another question. If you know the response Zn of t for this system is given like this, Fn of t by Kn 1 by this multiplied by 1 by 1 minus lambda, this is the forcing frequency, by omega n square sine lambda t. Right? Now what will be the responses for corresponding to two nodes? So how we can find it out? Like we have the value of the modal forces Fn of t, we have the value of omega n, that means the corresponding to two natural frequencies. We have the forcing frequency lambda, recall 20 hertz. Now 20 hertz or 20 rad per second, let's consider that lambda is 20 rad per second. Great. Now how we can solve it? We have that value of Fn, we have the value of Kn, we have the value of lambda, we have the value of omega n. We just need to replace it. So what is that F1? The magnitude of the first force. So that comes as 0.92 kilonewton. That comes as 920 newton. That directly I have put here 920, the magnitude of the force. Now what is the normalized Kn? So we have already calculated the value of phi transpose K phi here. The value is, the first one is 208 and second one is 916. So K1 and K2 value already we have. So K1 is 208, K2 is 916. And we have the forcing frequency 20. And here already we have calculated the omega, two modal frequencies 14 and 30, right? So just replace this, you will get Z1 is equals to minus 4.97 sine 20t. For your data, you just need to replace it. Like there 10 was the frequency, forcing frequency of these systems. Rest of the things like there was a little change due to I have changed this stiffness matrix. So there will be little change in frequency. Like instead of 19, you will have 20, 14.40, you will have some 15 or 13 around that, and instead of this you will get 29. So Z1 and Z2 we have now the values minus 0.83 sine 20t. These are the modal responses. So these are the two values. Now once we have the modal responses, we have the mode shape information phi 1 and phi 2. Can we find out the physical responses? Yes, precisely this is the next question. Calculate the modal response in the physical sense for two modes. Modal response, we know modal response x of t. Say for we want to consider the nth mode, it's nothing but phi n into zn. So the first mode x of t n, that means for the first mode 1 will be phi 1 z1. We have the phi 1 value. Phi 1 is nothing but the normalized mode shape, and x of t we consider phi 2m to z2 using mass normalized mode shape. They have specifically defined you need to follow the mass normalization mode shapes. So mass normalization mode shapes we have already calculated this part and this part. Z1 and Z2 we have already calculated on the previous slide. Z1 is nothing but this, Z2 is nothing but this. So we have for the first mode we have this response. For the second mode, we have this response. That your x1t, say let's say we have this is your two-DOF system. So first degree of freedom here, second degree of freedom here. So this one is, we'll say for example small x1 of t. This is your small x2 of t. So this x1 of t for the first mode will contain x1 of t and x2 of t. So x1 of t will be minus 0.097 sine 20t. At each time point, you will have this response. And x2t for the first mode will be minus 0.195 sine 20t for this. And for the second mode, you will get this for the two. Now, if we want to combine the two responses, what I need to do, that x of t vector will be nothing but your phi total vector into your z. So you will get the combination from two modes. Say x1 will be phi 1 1 z1 phi 1 2 z2, like this. We have already seen this kind of equation. So for now you just need to calculate the modal responses. That means xt1 and xt2, and you will get the answer in the form of vectors, and you just need to put it the right answer, right? So this example actually covers all the part of this model representation, all these things. So first quickly recap this example, and then we will go to next topic. So this example where mass stiffness and damping matrix, mass stiffness and modes of matrix were given. Also the model, also the forces, external forces which is acting on the system are also given. First, we need to calculate the normalized mode shape. For this mass normalization, we know it's nothing but phi divided by under root of phi 1 transpose m phi. If we want to do the normalization corresponding to phi 2, it will be phi 2 transpose m phi 2, and so on, so on. And then we need to calculate the modal frequencies. To calculate the modal frequencies, we have used this orthogonality property of the modal stiffness and mass matrix, and phi transpose k phi ultimately become omega n square, and omega under root of omega will give us the natural frequency of the system. Then we have the mass normalized mode shape. We have the forces acting on to degrees of freedom, we need to calculate the normalized or the generalized force is nothing but phi n transpose F. And they have particularly asked for mass normalized mode shape. That means you need to do all the calculations with respect to the mass normalized mode shape, whatever we have calculated, and using this we have calculated the normalized or generalized forces. Now once we have the forces, we can calculate the Zn value for Z1 and Z2. For these two we have calculated, and once we have the Z1 values, we can calculate the modal responses. Modal responses is nothing but your phi n into Zn. By this way we can calculate, or we can solve, or we can handle this kind of problem. So do you have any kind of questions? You can ask me. So with multi-degree of freedom system is clear now, right? How we can write down the modal responses with respect to the mode shapes and all these things. You can solve now any kind
Yes.
of problems.
Yes.
Yeah, and it's like quite easy to handle. Like if you have 5 degree of freedom system, and if you need to solve all those response using state space, uh, you can do it. And also in the modal coordinates, if we have larger number of freedom degree of freedom, then it will computationally help. Like you can solve that 5 degree of freedom system in modal coordinates. You have the modes of information. Or if you don't have, you just solve this characteristic equation. You will find out the eigenvalues, and that eigenvalues will be the mode shapes, right? Then you do the normalization things, and you can solve the responses. I will show you how we can do that. Okay, so we have one more question left, and then we will move to the MATLAB, and we'll see how we can get the responses of a multi-degree of freedom system. So the last example says calculate the frequency response function. We need to calculate the h omega. For omega is equals to 20 rad per second. It is given. Consider the damping ratio is 5%. K matrix, that means the modal stiffness, modal mass, and the uh, frequencies are given. Now, what will be the frequency response function? So here we already have discussed about the frequency response function. H omega is equals to 1 by mn omega n square, 1 minus omega by omega n square, minus I twice zeta n omega by omega n. That omega is the forcing frequency, and omega n are the natural frequencies. So if we want to calculate the frequency response function with respect to the nth mode, we need to consider the natural frequency of the nth mode and the forcing frequency. So this is the equation to calculate the frequency response functions. Now for h1 of 20, this will be 20, because we are calculating the frequency response function for omega equals to 20 rad per second. So h1 of 20 will be 1 by mn omega n square. Mn omega n square is nothing but your k. So the k 1. Now 1 minus omega by omega n, this is your forcing frequency given as 20 rad per second. This is the natural frequency here already given corresponding to the first mode, and I again put these values. This is your forcing frequency given, this is the natural frequency for the first mode. Now again, if we want to solve it little simplify it little bit, we will have answer like this. So for the second mode h2, if we want to calculate, again what we need to do, 1 by m2 omega 2 square, that means this part within the bracket 1 minus that omega is given as 20, but for the second mode omega n is given as 30.27 square minus I of, again do the same thing, 2 into 0.05, the damping ratio, multiplied by 20 divided by 30.27, divided by the denominator part. You need to write it again, 1 minus 20 by 30.27 square plus 2 multiplied by 0.05 multiplied by again 20 by you 30.27 square. Now you just simplify it and you will get this kind of term, and this will be your answers. Like in your question, the omega is given as 10, uh, and rest of the M, K, and C matrix you need to calculate it as per the previous example. There will be little change, but if you do the calculation following this procedure, you will have the answers. Okay. So do you have any kind of questions, or we will now move to the MATLAB and we will solve the problems. So let's quickly go to the MATLAB and let's solve one MDF system. Say let's say using in time domain. First, let's say time domain, and if we have time, then we will solve it in frequency domain also. So let me quickly share the MATLAB screen. Okay, is this MATLAB screen is visible? You can see the MATLAB screen, right? Sorry.
Yes.
Okay. So let's say we have a three-dop system and we want to solve this three-dop system using uh, we will go with the time domain response. That means we will use the Duhamel integral because we have already developed the Duhamel integral codes. Later on, I will show you how we can use the numeric beta and other techniques also. So let's say we have a three-dop system or 3 degree of freedom building. So M1, M2, M3, K1, K2, K3, and also we will consider a damping model that as per your classical damping model A0A plus A1K. Sorry, and we will apply some harmonic forces at each degree of freedom. Say x1, and here I will apply F1 is equals to some harmonic forces, say 10 sine some 20 t, and here also x2 f2 will apply some force, and here also x3 f3 will apply some force. So first what will we need? We need the responses, like what will be the x1 of t, what will be the x2 of t, what will be the x3 of t. That means what will be the displacement corresponding to three nodes, what will be the velocities corresponding to three nodes, and what will be the acceleration corresponding to three nodes. That means x dot and x double dot, we need to find it out. So first we need to define the properties. So let's say we have mass 10 kg, 10 kg, 10 kg, and stiffness. Let's say for the first case, stiffness I have provided 1200 uh, Newton, in Newton, obviously Newton per meter, Newton meter, and K2 1500 and K3 1200, right? Now what we need to do? We need to define the initial conditions. So initial displacement is given as, say, for the first degree of freedom system, the initial displacement is given as 1, then 2.25 and 1.23. You can change it, like you can start your system from absolute rest, so you can provide this matrices or these vectors as 0, and xd also provided a velocity, some velocity. Now we need to define the time array. So 0, we are starting from the 0, and we are considering the dt 0.01, and we will move to 60 seconds. So we can like change the time array as per our convenient, right? So first, what we need to do? We need to make the diagonal, that mass matrix. So mass matrix, we know it's a diagonal matrix. So mass will be diagonal of m1, m2, and m3. Now for the 3 degree of freedom system, we need to find out the K matrix. So K will be Q1 plus K2 minus K2 0 minus K2, K2 plus K3 minus K3 0, K3, K3 minus K3, K3. Now what we need to do? We need to find out the values of values of the mode shapes. So what do we do? We will do the eigen operation. So in MATLAB, we know that VD is equals to EIG. That EIG command will give you the eigen, do the eigen operation and give you the eigen values and eigen vectors. So V are the eigen vectors and D are the eigen values. So omega n, obviously, what will be the omega n? Omega n will be square root of this D omega square. Already we have solved using pen and paper, and we have seen that omega square are the eigenvalues whatever we have calculated, and 5 will be the eigenvectors. Okay, so we have now the mode shapes ready with us. Now what do we need to do? We need to define the initial conditions of the system in the modal coordinates. Like here we have discussed two methods. Either we can inverse this phi or we can use these values. So first, if we stick to this first approach, here z naught is inverse phi of x naught and z d naught is inverse phi of x d naught. Now we need to make the mass normalized matrix or the modal matrix, modal mass matrix. MD is nothing but phi transpose M phi. Now to use that damping model, we need to define in terms of alpha and the A naught and A1. So A, recall this matrix of the classical damping. What was the format or the sequence of the matrix? It's look like this. 1 by omega I, 1 by omega j A naught A1 is equals to 2 into zeta 1, zeta 2. And precisely we have done that. So let's consider zeta for first two modes 5%. So here A, to construct this AB, I have written it down 1 by twice omega 1, then again 1 by 2 omega 2 by 2. That's it. So C, now we can calculate the C or formulate the C matrix as per the classical damping model. C is nothing but A naught M plus A1 K. So these are the value of A naught and A1. Now we can calculate the, once we have the C matrix, already you have formulated using the Rayleigh damping method or the classical damping method. Now we can easily calculate the modal damping. So the modal damping CD will be phi transpose C phi eta n diagonal, already we know diagonal of CD, like phi transpose M phi divided by twice omega n. That means it will give the value of the second eta. Now what do we need to do? We need to define the forces. So here Ft, we have provided three forces: 2.5 sine 2t, 10 sine 6.5t, and 2.5 sine 15t at each degrees of freedom. So these are the external forces. So we need to normalize it. Fn is nothing but phi into Ft, right? So till now We have the modal information, we have the forcing information. Now what we need to do, we need to solve for the modal responses. That means we need to have that Zn values, right? So the Zn values we will use the Duhamel integral part to solve it. Already we have generated that Duhamel integral function file. Here if you provide m, k, eta, t and ft, it will give you the responses corresponding to that given values. So here we will precisely use that Duhamel integral. We will provide the omega n values, eta values and forcing function values, and it will provide me the Zn. Now once we have the Zn values, the xt, the physical response xt, will be phi into Zn. Now once we have all these things, we can plot this part, like plot t versus the first response or response or first displacement response corresponding to first degree of freedom, then displacement corresponding to the second degree of freedom, and then displacement corresponding to the third degree of freedom. That means we will have the we will have the displacement responses corresponding to first story, second story and third story, right? Now let's run the code and see whatever we have used giving us the results or not. Yeah, now we can see it has solved and given us the results. So first floor, you can see it has that minimum deflection values, and for the third floor we have higher deflection values obviously. Now it also follows the sinusoidal nature, but it has different frequencies particular to different nodes. That why we have mixed frequencies over the responses. And if we want to see the calculations, like what are the calculations, here we can see the calculations. Right, these are the natural frequencies of the system. First natural frequency comes as 5.0529, second natural frequency comes as 13.80, and third natural frequency comes as this. And corresponding mode shape are this. This is the first mode, this is the second mode, and this is the third mode, and complete it gives us the modal matrix. Now these are the initial conditions whatever we have calculated. Then this is the, you can see the modal matrix, and we know it should be the identity matrix, and you can see it also become the identity matrix. And eta we have considered for two modes 5%, and for the second for the third mode using this method it has considered eta 3 and formulate the C matrix. So eta 3 it has calculated 0.0646, that means almost 6.46%, and we have the CD. Now once we have all these things, we can calculate the responses. Now instead of 5%, if in 5% we have the maximum response, like corresponding to 0.4 or 0.3 maximum in the steady state part. If we look at the steady state part, we have the maximum response or peak response 0.3. Now if we change that damping property, let's see what happens. Like instead of 0.2 0.5, let's say we use 2% of damping, 0.2 and again 0.02. So obviously what will happen, I'm decreasing the damping value, obviously the response will increase, right? So now let's see, is it increasing or not? Yeah. So 0.3, we can see that 0.3 was the steady state response. Here we can see the responses has increased a little bit, right? Now here we have used like the values of forcing function. Now corresponding to that, like that phenomena resonance. So here we have seen that the natural frequency of the systems are calculated as 5, 13 and 21, and the forcing frequencies we have provided 2, 6.5 and 15. Now if we change this forcing frequency to that frequency, we will have the resonance. Say 5 near about. I'm just want to add this, just show you the 13.8 and 25. 13.5 and 21 and 21. Now let's see. Yeah, the resonance will occur. The responses become unbounded and continuously it will increase, right? So that's why we need to take care of the resonant frequency, because the maximum responses will occur at that frequencies. Now, if we want to increase the forcing frequency higher, then you will see that responses will again come down. Say in instead of 5, if I put 15 over here, and instead of 13, if I put say 33, and instead of 21, if I put 29, then we cross the resonance zone and we will have again the you know, steady state kind of responses, right? So this is very important to take care of the resonance frequency. If the resonance occur, we will have the maximum dynamic responses, and corresponding the values will be maximized by this effect of the responses, right? So by this way we can solve, and we can have the responses. Like here I have plotted only the displacement responses, right? Now if I want to plot the velocity and acceleration, what I need to do? So these are the displacement responses corresponding to each flow. Now if I want to, you know, plot the acceleration and velocity responses, what I need to do? What I need to do? We have the displacement x, say x1 of t, x2 of t, x3 of t. So what I need to do? I need to differentiate diff command. You can use x1 of t. What you will get? X dot of t. Again, you use double diff command with that, or just diff of x of t. You will get x double dot of t. You can do the exercise and check whether how the responses will look. The differential command, if you forget how to use the diff command, just here go to that command window and doc diff. The MATLAB will give you how to use that diff command. So y is equals to diff of x. Now if you use that command, you will get the acceleration response and velocity response corresponding to that particular nodes. Okay, so do you have any kind of questions? Like we can solve it in frequency domain also. So today we ran out of time, so today we will not discuss that. We will discuss it on the next class, and we also will solve using different numerical integration techniques to solve the multi-body or that multi-degree of freedom systems. So do you have any kind of questions till now? Okay, so let's quickly recap what we have done today, and then we will close our sessions. So first, we have spent time or a few times on these damping models, particularly Rayleigh and Caugh damping model, how we can use this damping model to get the responses, and then we move to the force vibration due to, or that, you know, damped force vibration part of MDF system, where we have seen how we can solve in modal coordinates. That means we need to find out the mode shapes and the generalized coordinates or the modal responses. Once you have these modal responses and the mode shape information, you can easily calculate the modal responses using the equation phi n into z. And also we have seen how we can, you know, convert it into the frequency domain, and using the frequency response function, how we can calculate the responses. Also, here in using the frequency response function, we need to invert that equation. So just think, we have a 10 degree of freedom system or 22 degree of freedom system. So that h omega, that means the uh, frequency response function will look huge, gigantic. So it will be a little heavy to compute, or we need to give more computational cost to it, computational effort to it more particularly. So that's why we have seen that how we can represent it using that modal coordinates, so and mode shape information. So we have seen, okay, using this representation we don't need to invert that equation, and it will be little less heavy compared to that inversion for every omega we need to do it. And then we have solved one series of example where we have first seen that how we can do the mass, or how we can have the mass normalized mode shapes, and then how we can get the modal frequencies if the mode shape information and all other information like mass matrix, stiffness matrix, and forcing information are given, how we can get it just using the diagonal properties of the mode shape and all these things. And then we have calculated the generalized force for each node, and then generalized responses for each node, and and how we can get the modal responses for corresponding to first mode, corresponding to second mode, and so on. So that's all for today, right? And then we solved one multi-degree of freedom system using Duhamel integral technique in modal coordinates. So here you can see, and that Duhamel integral part already we have generated this code. Also, you can use this Duhamel integration using simple command conv. Already I have showed you how we can use that conv function. You don't need to write down this function file. The already inbuilt function is there. So go back to that Duhamel integral video session. You can see I have explained how you can use that convolution function within that MATLAB, and you can directly convolute it, and you can get the responses using that Duhamel integral, right? So do you have any kind of question, you can ask me, or else we can conclude our session here, and we will meet on the next class or next sessions. So Sovik, do you have any question?
No.
Great. Then let's close today's session, right? Thank you. We'll meet on next interaction session, possibly on 1st of April. Yeah, yeah, April, on the April Fool day. We'll meet. Okay, thank you.